This is Anika Chawla presenting Physics 2211, Lab 2 on gravity and drag. So on Earth, the acceleration due to gravity is negative 9.8 meters per second squared for objects close to the surface of the Earth, and this means that ideally if an object is dropped from rest, it will accelerate at a constant rate. And drag force is a mechanical force that occurs when a solid object moves through a fluid, and it works in the direction opposite to the object's motion. It's a form of friction, and it occurs when the object's interacting with the fluid, which in our case would be air. And when an object is falling, gravity and drag will act in opposite directions and create a net force when they are unbalanced. So the objective of this lab is to explore how just gravity and then gravity and a drag force together impact the motion of an object. To determine this, an object's motion was recorded in a video and then analyzed using Tracker, and then a computational model of the object with just gravity acting upon it was created under ideal conditions such as no drag, and then a second computational model with gravity and drag acting upon the object was created. And for the second computational model, the motions should be similar to the motion in the experimental model. So here are the materials. And here's the video. It goes by kind of fast, I'll play it a few times. But as we can see, the object is accelerating. And so here's all the code for reference, but I'll explain it more in depth. But this is the computational model with just gravity acting upon the object, and it's a fitting computational model because it's able to replicate ideal conditions and how the object would move if there were no force except for weight acting upon the object. And as we can see, the position versus time graph is concave down and the velocity versus time graph is a constant negative slope. So both these indicate a constant acceleration or constant net force in the downward direction. And this is a computational model with gravity and drag acting upon the object. This is fitting because we can predict just gravity and drag acting upon the object and no other forces, which we can always do in the real world. And the position versus time graph is concave down, and the velocity versus time graph is not completely linear. But as we can see, that it's less concave down than the model with just gravity. And this indicates a net downward, unbalanced, non-constant force, which is indicative of gravity and drag acting upon the object. So here's the code explained more in depth. The initial mass of the ball is object was 0.003 kilograms, and then the initial position and velocity was 0. And the timestamp is determined from the video, and the acceleration due to gravity is 9.8 meters per second squared. And the ball's velocity, the object's velocity was determined using the velocity update formula, and the object position was determined using the position update formula, as can be seen here. And for the model with just gravity acting upon it, net force is weight, or negative mg, multiplied by j hat for direction. But then for the model with drag force and gravity acting upon it, weight is still negative mg times j hat. And then drag force is b times the magnitude of the velocity squared times j hat. And b was determined through trial and error until the computational model fit the experimental model. And the net force is weight and drag force, and as we can see, the weight and drag force have different signs, so they're in opposite directions. So here's all the data for reference, and here's the graph, which will be explained more in depth. So as we can see, the graph indicates that the computational model with just gravity acting upon it had the greatest magnitude of net force and the greatest change in position, and the computational model with gravity and drag force and the experimental model are almost collinear, and the magnitude of the net force is less than the model with just gravity because drag force is acting in the direction opposite to the object's motion, while gravity is what's causing the object's motion. So the force with just gravity is constant, but the experimental and computational model with drag are not constant, as we can also see in the graph. And so the graph represents the results that we expected, and it effectively demonstrated the impact of drag. So the object's terminal velocity is when the drag force and gravity force are balanced, which means there's a net force of 0. So the computational model with drag and the experimental model could potentially reach a terminal velocity if they had enough time and they were dropped from a higher point, but they didn't in our model. And terminal velocity is when the net force is 0, and at this point the object will move at a constant speed, and that speed is the terminal velocity. So if the object was initially thrown downward, the terminal velocity would be different from when the object was dropped, because it would start with initial downward velocity and downward force, so the terminal velocity would be higher than if it was dropped from rest, and this is supported by the computational model because when initial downward force and velocity is input into the program, the terminal velocity increases.